Welcome and Namaste. Welcome you to the session 19 of B.Sc third semester chemistry program. In this session 19, we'll discussing about Vant-Hoff equation isochore and Clausius-clayperon equation and some of the problems on applications of Clausius-clayperon equation. With this brief introduction, I present my lecture before you. In thermodynamics 2, the continuation of this, derivation of Vant-Hoff reaction isochore and temperature coefficient, and Clausius-clayperon equation and its application, and for which we will not derive thermodynamic derivation. He has studied in previous classes about Gibbs-Helmholtz equation at constant temperature and pressure and its derivation, Vant-Hoff reaction isotherm, its derivation, numerical problems on it. And what are learning objectives of this session are to study the need of derivation of Vant-Hoff isochore, to study the need and importance of Clausius-clayperon equation, and to study the application of delta TB and delta TF determination. And what you will study at the end of this course or session are you are able to derive the expression for Vant-Hoff reaction isochore. You are able to derive the expression for Vant-Hoff reaction and Clausius-clayperon equation to be mentioned and its applications. What you should know before start this session are you should know the Gibbs-Helmholtz equation and you should know the phase change process and you should know the concept of change of temperature, pressure and volume during the process. And also you should know the concept of depression in freezing point and elevation in boiling point. With this brief background, we'll start discussing about the today's concepts of session 19. The first one is derivation of Vant-Hoff equation isochore. As you have seen, the equation from Vant-Hoff reaction isotherm, it can be written as the standard free energy change is equal to minus RT ln Kp. Let it be this equation as 1. Hence, this equation can also be written as, you know, dou of delta Z naught by T over dou T is equal to R into d ln Kp by dt. Let it be this equation as 2. From Gibbs-Helmholtz equation, we know that this term dou of delta Z naught by T by dou T is equal to minus delta H naught by T square. Now, this value is minus delta H naught by T square, and further you can see from equation 2 and 3 d ln kp by dt is equal to delta H naught by RT square. Let it be this equation as 4, where delta H naught is the standard enthalpy of the reaction. This equation is called Vant-Hoff equation or isochore. Now, the integrated form of the Vant-Hoff equation is the integration of equation 4 depends upon the manner in which delta H naught depends upon the temperature. If over a short temperature range, delta H naught is assumed to be temperature independent, then the integration of equation 4 gives you the integration of d ln kp is equal to integration of delta H naught by RT square into dt. This dt in the denominator, if you send it to here, it is dt. Then delta H naught by RT square integration of dt by t square, let it be this equation as 5, or this equation also be, that is the integration of d ln kp gives you ln kp is equal to minus delta H naught by RT and the integration constant plus I, where I is the constant of integration. According to equation 6, a plot of ln kp, this is versus 1 by t, gives you a straight line with slope minus delta H naught by R. Thus, from the slope, delta H naught can be determined, that is equal to delta H naught minus R into slope. So, from this Vant-Hoff reaction isochore, you can calculate from the experimental result the standard change in enthalpy of the reaction. Then, if equation 4 desired to integrate between two temperatures, that is T1 and T2, when the equilibrium constants are Kp1 and Kp2 respectively. Then, assuming that delta H naught is constant over the temperature range, we obtain the integration of Kp1 and Kp2 d ln Kp is equal to delta H naught by R integrating over T1 to T2 dt by t square, or this equation gives you the solution ln kp2 by kp1, this is integration form of this, is equal to minus delta H naught by R minus 1 by t square minus of minus 1 by t1. Further, this simplification gives you delta H naught by R T2 minus T1 by T1 into T2. This is the final integrated Vant-Hoff equation isochore. Now, this equation 9, from this equation, if delta H is known, then knowing the value of Kp1 and Kp at T1, the value of Kp2 at T2 can be determined. Also, if Kp1 and Kp2 at T1 and T2 respectively are known, delta H can be calculated. And as you look at the above equation 9, this is similar to the temperature coefficient. The ratio of the equilibrium constant at a higher temperature and equilibrium constant at a lower temperature, this is equal to delta H naught by R and T2 minus T1 by T1 into T2. As this equation is similar to the Arrhenius energy of activation equation, where it gives you the temperature coefficient of the rate constants. So this equation is also an equation for temperature coefficient. In this equation, if T1, T2 are known, delta H naught is known, and R is known, you can calculate the ratio of the equilibrium constant for the reaction which is in equilibrium. Or Kp1 and Kp2 are known, R is known, that is gas constant 8.314 joule per Kelvin per mole. If T1 and T2 are known, you can calculate delta H naught at two different temperatures provided their equilibrium constants are known. Okay. The next concept is Clausius-clayperon equation. This equation is very, very important and it is applicable for the system which exists in an equilibrium with two different phases at constant temperature and pressure. Either liquid to solid equilibrium, or liquid to vapor equilibrium, or solid to liquid equilibrium, any kind of these two phase changes from liquid to vapor or liquid to solid, these phase changes, during these phase changes, we can have to calculate the thermodynamic parameters. Suppose a system exists in two phases, A and B, in equilibrium with each other at constant temperature and pressure, that is A equilibrium B. The equation, that is dP by dt, that is change in pressure over the change in temperature, is equal to delta H naught H by T into VB minus VA, that is product minus reactant, that is VB minus VA. This is important. If the two phases considered are liquid and vapor, suppose A is a liquid and B is a vapor, and this equation can be written as dP by dt is equal to delta HV by T V minus VL. So here delta HV is a change in enthalpy for vaporization process, and VV, that is molar volume of the vapor minus molar volume of the liquid, and this is the temperature at which this process is taking place from liquid to the vapor. Then, as I told you, delta HV is the enthalpy of vaporization, molar volume of vapor, and molar volume of the liquid. And the same equation can be written for the liquid to solid equilibrium. Then liquid gives you the solid, that is delta HF divided by T into Vs minus Vl, the molar volume of the solid and molar volume of the liquid. It is the change in the enthalpy of the fusion. Yes. Then the above equation can be integrated, and integrated form of Clausius-clayperon equation can be written for liquid to vapor process. The equation can be written as log P2 by P1 is equal to delta HV by 2.303 R into T2 minus T1 divided by T1 into T2. Now, P1 and P2 are the vapor pressures at temperature T1 and T2 respectively. Delta HV, that is molar heat of vaporization, that is in terms of joule per mole, this is, and R is a gas constant, that is 8.314 joule per Kelvin per mole. P1 and P2 are pressure at T1 and T2. Now, applications of Clausius-clayperon equation, you can calculate molar heat of vaporization from the integrated Clausius-clayperon equation, and you can also calculate the effect of pressure on boiling point to study the effect of temperature on vapor pressure of liquid. Now, the next thing is to calculate some of the numerical problems on this Clausius-Clayperon equation, both integrated and non-integrated form. I will start with solving some of the numerical problems on this Clausius-Clayperon equation. I will read the problem. Calculate the value of dP by dt for the water, liquid to solid, that is ice, system at 0 degrees Celsius. Delta HF, that is for water, is 6007.8 joule per mole, where 1 joule is equal to 9.87 into 10 to the power of minus 3 dm cube atmosphere. Molar volume of water is equal to 18.0 cm cube and molar volume of ice is 19.63 cm cube. And as we start solving this problem, in the problem you have to look at what is being calculated. That is most important. What is being asked to calculate? That is dP by dt. Okay, to find what? To find dP by dt. That is how much? Okay. To calculate this dP by dt, you know the equation, the formula, that is delta HF divided by TF Vs minus VL. This is the equation. Okay. And this is a formula to calculate this dP by dt for which process? For liquid to solid equilibrium. That is important because this is water and this is ice. Right? For this equilibrium, the equation can be written as this. Now, to calculate this, we should have a delta HF. Okay. Now, we have to find out the given values. What are the given values? Delta HF is equal to what? 6007.8 joule per mole. Right? That is important. Then, next, what is the data? Molar volume of water, that is VL is equal to 18.0 cm cube. Then Vs, that is 19.63 cm cube. Okay. Now, these are given. Next, what is required? TF. TF, that is equal to 0 degrees Celsius. This you can write as 273 Kelvin. Okay. Now, this 18 cm cube and 19.63 cm cube. See, and what about this 6007.8 joule per mole? This you can convert this into what? Where 1 joule is equal to 9.87 into 10 to the power of minus 3 dm cube atmosphere. Therefore, this delta HF further can be written as 6007.8 joule per mole into 9.87 into 10 to the power of minus 3 dm cube atmosphere per joule. That you have to write. And further, since it is in dm cube and this 18 cm cube can be converted into dm cube as how you write, that is 0.018 dm cube, and this is 0.01963 dm cube. Okay. Now this value you have to place in place of delta HF, and this 0.018 for VL and VS for 0.01963 and TF, that is 273. Now you can substitute all these values, that I will write dP by dt is equal to, what is that? 6007.8 joule per mole into 9.87 into 10 to the power of minus 3 dm cube per mole per joule, right? Divided by what? TF, that is 273 Kelvin. VS, that is how much? VS is 0.01963, right? Minus 0.018. What is the dm cube per mole? Per mole. Now this mole and this uh, sorry, this is dm cube atmosphere, I'm sorry, and this per mole gets cancelled, and further what is that? uh, Joule, this joule and this per joule gets cancelled, and what is remained? And this dm cube and this dm cube gets cancelled, and what are the remaining unit in the Kelvin and atmosphere? So what is the total unit? It will be atmosphere per Kelvin it will be. So you multiply 6007.8 into 9.7 into 10 to the power of minus 3. That will give you 15.89 divided by this 0.01963 minus 0.018, subtract these two and multiply by 273, gives you 0.44499, right? Then what? This gives you 133.23 atmosphere per Kelvin. Okay, this is what? The answer is 133.23 atmosphere per Kelvin. Now, this is the final answer. Next, we'll go for the other problem, that is vapor pressure of water at 95 degrees Celsius and 100 degrees Celsius are 634 mm and 760 mm respectively. Calculate molar heat of vaporization, that is delta HV, of water between 95 degrees Celsius and 100 degrees Celsius. And what is asked? Calculate the molar heat of vaporization. That is most important. To find what? To find what? Delta HV. This is very simply from Clausius-clayperon equation. And to calculate this, what are given? Right? So what is the equation from the Clausius-clayperon equation? 2.303 R into T1 into T2 divided by T2 minus T1 log of P2 by P1. Okay. Now this need to be calculated, and R, what is R? Given, right? It is not given, but it is known, 8.314 joule per Kelvin per mole. That is 1. And T1, what is T1? T1 is 95 degrees Celsius, and T2 is what? 100 degrees Celsius. Next is P1. P1 is 634 mm, and P2 is 760 mm. And these are okay. Now, since the gas constant is in Kelvin, you can convert this into plus. You can add 273. You will get what? 368 Kelvin. And plus 273, you will get how much? 373 uh, 373 Kelvin. Okay. P1 and P2. This pressure 634 mm at T1, P2 760 mm at T2. Now P1 is known, P2 is known, and T1 and T2 are known. Just and R is also known. You can calculate delta HV. Now, how you can calculate this? Now, delta HV is equal to you know that equation already, that is 2.303 into 8.314 joule per Kelvin per mole. This is the unit. And T1, what is T1? T1 is 373 into 368 divided by 373 minus 368. Okay, then here is Kelvin, here is also Kelvin, and I can take the common here, Kelvin here, and log of what? 760 mm divided by 630 mm. This all gets cancelled. And what about the unit? And this K and this K gets cancelled, and this K and this per K gets cancelled, and the remaining unit you should know, this unit should be finally joule per mole, because delta HV unit is in terms of joule per mole. Now you can calculate 2.303 into 8.314 into 373 into 368. I will write as it is 2.303 into 8.314, right, into 373 into 368 divided by 5. Then log of what? Log of 760 divided by 630. Okay, and final unit is joule per mole, that I will write here. Then is equal to how much? You can write the total solution of this is 2525642.65 log of 760 divided by 630 joule per mole. Then further, you can take log of 760 by 630 and it will be 2525642.65 into what? Into 0.07872 joule per mole. And final answer is how much? 41,373.59 joule per mole. Then, sorry, this is not joule per mole. And, no, sorry, this is not. Okay, then in terms of kilojoules, 41.373 kilojoules per mole. Okay, the answer is delta HV is equal to, this is the answer. Okay, then the third problem is the vapor pressure of water at 95 at 100 degrees Celsius is 760 mm, and what will be the vapor pressure at 95 degrees Celsius? The heat of vaporization of water in this temperature range is 41.27 kilojoules per mole. Okay, it is similar to the previous problem. What is asked here? What will be the vapor pressure at 95? First, let me note down what are given, right? 100 degrees Celsius is given, right? And other one is 95 degrees Celsius is given. Okay, so I will write this as T2 and I will write this as T1. And the pressure, vapor pressure of water at 100 degrees Celsius is 760 mm. That I will write as P2 as 760 mm. And what will be the vapor pressure at 95 degrees Celsius? That will be as P1, that we don't know. So the heat of evaporation of water, that is delta HV is equal to 41.27 kilojoules per mole, or it is 41,270 joules per mole. Very simple. Okay, what is the formula you have to use to calculate this problem? Log of P2 by P1 is equal to delta HV by 2.303 into T2 minus T1 divided by T1 into T2. Okay, this is the solution. Now, what is asked here? Just we'll continue with this. Log of what 760 divided by P1 as it is, then 41,270 divided by what 2.303 into 8.314, then about temperature 373 minus 368 divided by 373 into 368. All units will be cancelled here, right? Then what is the final answer? That 41,270 divided by 2.303 into 8.314, 5 divided by 137,264. If I multiply these two, 373 into 368, and further multiply all these numerator quantities and denominator quantities, what you will get? 206350 divided by 2628 213.29, then is equal to 0.07851. Right? What is this? This is log of 760 divided by P1. Now uh, further log of 760 minus log of P1 is equal to 0.07851, and log of 760 is 2.88 minus log of P1 is equal to 0.07851, and minus log of P1 is equal to 0.07851 minus 2.88, and this will give you minus log of P1 is equal to how much will get minus 2.80149. Then this and this is cancelled, and log P1 is equal to 2.80149, and further P1 is equal to anti-log of what? 2.80149, and further P1 is equal to 634.30 mm. So this is the answer. Okay. Next problem is ether boils at 33.5 degrees Celsius at 1 atmosphere. At what temperature will it boil at pressure of 650 mm, given that heat of vaporization of ether is 369.86 joule per gram? Now, the ether boils at 33.5 degrees Celsius. I will write here. Boiling point temperature of ether is 33.5 degrees Celsius. At what temperature will it boil? Okay. At 1 atmosphere. At 1 atmosphere is 760 mm. Right? That is P. I don't know this. This is T and this is P. Now 650 mm is given, that is a lower pressure. Okay, therefore I will write this as P1, and this is P2, and this is T2. And at what temperature? That means T1 is being asked. T1 is being asked in the problem. What is that T1? And what is next is given? Heat of vaporization, that is delta HV is given, that is for ether 369.86 joule per gram. Okay, now you can convert this into joule per mole, and the molar mass of ether, that is not given. Actually, it should be in the problem. Molar mass of ether is equal to 74 gram per mole. Okay, so you can convert every datas. Here T2, that is 33.5 plus 273 will give you how much? That is 306.5 Kelvin, and T1 is not known. Then P2 is equal to 760 mm, and P1 is equal to 650 mm. That is as it is. Then delta HV, that is most important, 369.86 joule per gram. That you can convert this into joules. That is, you can multiply by 74 gram per mole, right? Per mole, right? You can just strike out this gram per mole, right? Is equal to how much? It is 27,369.84 joules. This is what is called as joules per uh, mole it is. Mole. That what we have converted, joule per gram is converted into joule per mole. Now, you can substitute these values in the equation of what? Clausius-Claperon equation. Log P2 by P1 is equal to delta HV divided by 2.303 R, then T2 minus T1 divided by T1 into T2. Okay. Now, log of what is that? 760 mm divided by 650 mm. Okay. Then delta HV is how much? 27,316.84 joule per mole divided by 2.303 into 8.314 joule per Kelvin per mole units, right? Into T2 306.5 K Kelvin minus T1, I don't know this, then 306.5 into T1 because T1 is unknown. Now you can solve all this. This will give you around 4.66 into 306.5 minus T1 divided by 306.5 into T1, right? And this value, log of 760 divided by 650, will give you 0.0679. Then further, 0.0679 is equal to what? This already we have written this, and further 1,428.29 minus 4.66 into T1 divided by T1, right? And further, 0. This T1 can send it here, 0.069 into T1 is equal to 1428.29 minus 4.66 T1. And further, 0.0679 T1 is equal to 1428.29 minus 4.66 T1. Then 1428.29 minus 4.66 T1 is equal to 0.0679 T1. Then 1428.29 is equal to 0.0679 T1 and plus 4.66 T1. Now 1428.29, we can take T1 common here, 0.0679 plus 4.66. Then 1428.29, and the addition of these two will give you 4.72 into T1. Now T1 is equal to 1428.29 divided by 4.72. So further, T1 is equal to 2.10 Kelvin it is, and further you can convert this into degrees Celsius. 302.10 minus 273 will give you T1 is equal to 29.1 degrees Celsius. This is the answer. In Kelvin, it is the answer. Okay, the T1 is 3.2 10 Kelvin. The ether boils at 650 mm pressure. Okay. Now, these are the four numerical problems we have solved on Clausius application of Clausius and Clapeyron equation. Now, we are coming to the multiple choice questions. The equilibrium constant for the reaction N2 gas plus 3H2 gas gives you 2NH3 gas is 1.64 into 10 to the power of uh, 1.64 into 10 to the power of 4 at 273 Kelvin and 0.144 at into 10 to the power of 4 at 773 Kelvin. Calculate the heat of formation of 1 mole of ammonia from its elements in this temperature range. So given R is equal to 8.314 joule per Kelvin per mole. This is per Kelvin, this is per mole. And what is this is on the basis of Vant-Hoff reaction isochore, that is temperature coefficient log Kp2 by Kp1 delta H by 2.303, and here two temperatures are given 673 and 773, and Kp1 and also Kp2 are given, and what is to be calculated? Calculate the heat of formation. Okay, you can interchange this formula and you can calculate delta H provided T1 and T2 are known. Okay, you try for the answer, and now we have to look for the options. A is the option A, minus 105,226.93 joules for 2 moles and minus 52,613.465 joule per mole, and option C minus 12574.91993 calorie per mole, and option D all of the above. Since it is in terms of joule per mole, and we have to check for the answer, that is minus 12574.91993 calorie per mole. And second question, Vant-Hoff reaction isochore is a variation of equilibrium constant with temperature, variation of equilibrium constant with pressure, variation of equilibrium constant with volume, variation of equilibrium constant with temperature. Now we have to find the answer. This is variation of equilibrium constant with temperature at constant volume. And the option 3 is the Clausius-Clayperon equation is given by, for liquid vapor equilibrium is the equation option A, dP by dt is equal to delta HV by VV plus VL, and dP by dt is equal to delta HV by T into VV minus VL, and dt by dP is equal to delta HV by T into VV plus VL, and dt by dP is equal to delta HV by T into VV plus VL. And remember the Clausius-Clayperon equation and integrated form, and now find the answer. The option B is the answer. During phase transition like vaporization, melting and sublimation, pressure and temperature remains constant, volume and entropy changes, and both of the mentioned and none of the mentioned. During vaporization, melting and sublimation, definitely the entropy should be changes, and volume also changes provided pressure and remains constant, and hence the option is both of the mentioned. If the vapor pressure at two temperature of a solid phase in equilibrium with its liquid phase are known, then the latent heat of fission can be calculated by Maxwell's equation, Clapeyron-Clausius equation, van der Waals equation, and Nernst heat theorem. Okay, you know, when there is a change of phases between two temperature, it should be Clapeyron-Clausius equation. The option B is a correct option. Thank you. This is the end of this session 19. Hope the concept of Vant-Hoff reaction isochore and the Clausius-clayperon equation and its application, and the problems based upon the Clausius-Clayperon equations have been discussed. I hope these all points are very clear to you. Thank you. We shall meet in session 20. Have a nice time.